Go.
My name is Michael Orr. My partner Jose Franco is taping. This is our practical project for test 3. So for this project, we combined a 555 timer, making I believe an astable multi-vibrator, and we incorporated a rectifier as well as a Zener diode into the circuit. So the idea is here, you're taking a 120 volt current from a plug. It comes into the rectifier here, and the rectifier then converts it to DC power, which is then sent through the Zener diode, which regulates it down to 6.8 volts, which then powers our 555 timer circuit. And so what our circuit is doing is illustrated through the LED there, it is a flashing LED. The speed of the flash is controlled by the size of the capacitor here. So we actually, when we started out with a 10 UF capacitor, and we thought we built this wrong because the LED would not flash, but it turns out that just takes so long to it takes so little time to charge that it blinks so fast you can't even see it. So we actually had to up it to a 470, I believe, which gives it this nice steady blink, which is good for illustrating what we're trying to do here. So this is actually the printout of how the circuit actually works. So power here to our transformer, and then comes in here, step down to I believe 24 volts here, goes into our rectifier here, and that's the rectifier with the diodes like that. Then DC power comes out, DC negative comes out this side, DC positive comes out here, comes out, hits another capacitor here for, I believe, smoothing purposes, comes here to the Zener diode, which, like I said, regulates it down to a steady 6.8 volts, and then comes into a regular 555 timer circuit. Like I said, we have it going out to an LED here. So we did some calculations here. Most of our calculations are going to revolve around the transformer part of things here. So we know that it has 120 volts VRMS, which is root mean square, and to figure out the peak voltage off of that, peak voltage is VRMS equals 0.707 times voltage peak. So we can just reverse that around, knowing what we know. So it's 120 VRMS equals 0.707 times voltage peak. We can divide both sides by 0.707, giving us 170 volts for our voltage peak. Then we have the turns ratio of the transformer, which we're stepping down 120 to 24 volts. So that makes it a 5-to-1 step down. Then we also figured out the period of primary frequency. So that's how many times the AC is making its full loop on the oscilloscope. So that is 1 divided by the hertz, or the frequency of your AC power coming in, and it's 60 hertz. So 1 divided by 60 hertz equals 0.016 seconds per cycle on that. So that's our period of frequency. Then we also figured out the secondary peak voltage. So this would be the primary, this is the secondary on the transformer. And so we knew that the 18.2 was the voltage VRMS for the secondary. So same thing like we found for the primary side, voltage peak equals VRMS divided by 0.707, which means our voltage peak on the secondary side is 26 volts, I believe. And then we also figured out the peak-to-peak voltage, so that's the total up on the sine wave as well as the dip on the sine wave on the oscilloscope. So our secondary peak-to-peak voltage would be V peak-to-peak, that's what VPP means, equals VP, voltage peak, times 2. So our VPP equals 26, which is our voltage peak, times 2, which our voltage peak-to-peak on the secondary is 52 volts. And that is our project for test 3. Thank you.